speaker is again from Malga, is Jonathan Chirinos Rodriguez, and he's going to present learning resolvent operators. Please, Jonathan, the stage is yours.
Good morning, everyone. Okay, so first of all, I would like to thank the organizers for a very nice conference in a super nice place. And I also like to apologize because I think that let's say the content is a bit much more technical than the one just at the start. So I didn't know that there were so many master students, so that this may be a problem. Okay, and this was, let's say, a joint work which could also be entitled Learning Fermi Non-Expansive Operators. And it was done during a secondment period that they had at the beginning of the year in the University of Graz, together with Professors Christian Bredies and also with a PhD student, which is called Emanuele Naldi at the University of Braunschweig. So the starting point and let's say the main objective of the talk is to do denoising. So let's say the most simple example of an image processing problem, where let's say you as a user, you have a noisy image, and you want to, let's say, find an algorithm to reconstruct it in such a way that it is as close as possible to the original one, which you don't have access to. As both my colleagues Luca and Alessandro explained yesterday, let's say the mathematical formulation of this problem is the one of inverse problems, where you have access to, let's say, to a measurement via a corruption operator A and possibly a noise. The case of denoising is quite simple because you don't have the operator, but you don't have access to, let's say, to the original image. So you want to reconstruct the original image by only having access to, let's say, to the measurement. And the problem is given by the idempoteness of the matrix A. In any case, let's say that what we want to do is that we want to, let's say, in order to, let's say, get rid of this, let's say, idempoteness, what we want to do is that we want to solve this variational problem, which gives stable solutions by considering this function here, which is known as, let's say, which is known as a regularizer, and it has many utilities apart from giving, let's say, the stability of the solution, but it also, let's say, you can wisely pick it, let's say, choose it, since you can also, let's say, ask for it to have some kind of a priori information about the problem that you have. For instance, if you are solving a denoising problem, you want R to be, so the value of R to be bigger when your image is too noisy, and you want the function to have low values when your function has, let's say, a low amount of noise. Okay, so let's say, a way to solve this problem when the function is proper, convex, and lower semi-continuous, let's say from a very convex optimization point of view, you can think of solving this problem as this, let's say, inclusion problem, where one can think of it as so let's say if you have a function and you want to find, let's say in the smooth case, if you have a function and you want to find a minimizer, you compute its derivative and look for, let's say, and you look for critical points. In the convex analysis case, the function R may not be differentiable, and therefore you consider this, let's say, this operator, this multi-valued operator, which is known as a subdifferential of the function R. So let's say it's a generalization, and it not only has one value but many values depending on the function. So okay, so you think of this fixed point equation where sigma is only a step size. Or let's say in a more equivalent way, what you do is to solve let's say this fixed point equation, where you are introducing here the proximal operator that for instance Cesare was mentioning at the end of the talk before, where you are well, indeed this part here is the gradient of the function, because this part is differentiable, and let's say in the prox you are including, let's say, the subdifferential of the function. When when the function is proper convex and lower semi-continuous, so when a function belongs to this space, I will always say proper convex and lower semi-continuous, you can write the proximal operator in this way. And this exact formula, this closed form formula, is known as the resolvent of the operator R. Okay. So the main problem of this fixed point equation is that the proximal operator, as I'm saying here, is not always computable. Indeed, there are when there are proximal operator papers related, a big assumption is typically that the proximal operator is, let's say, in some sense easy to compute. But since the idea that I want to, let's say, ask myself whether what can I do if I don't have access to such proximal operator. So I wonder myself whether I can, in some sense, construct or learn, which is indeed the title of the talk, the proximity operator of any given convex function or of any given regularizer that I have. So if we come back to the fixed point equation before, this is known as, let's say from an iterative point of view, this is known as a graph prox, as Cesare was saying, or forward backward algorithm. And the idea is that this is since given the properties of the regularizer, this algorithm is known to be converging. The question is whether you can, let's say, change this proximal operator by any kind of operator, by, let's say, substituting it. In the past years, this has been a very, very important, let's say, topic, and these topics are called, let's say, these topics, let's say, titled in the plug and they are called plug and play methods, where instead of the proximal operator here, you introduce any kind of denoiser or any kind of neural network here, so that this, let's say, in order to achieve good performance in your process or whatever you want to do. Let's say the main problem and the main issue of such approaches is that there is a big lack, first of all, of theoretical guarantees in the sense of convergence, and the other lack of theoretical guarantees comes from the fact that, so let's say that the main, the most important thing of the reason why this algorithm is converging is because the proximal operator of this convex function is maximally monotone. And let's say the proximal operator has a very important property, and such property is difficult to ensure when you are plugging here a neural network. Okay, so let's say that the main motivation of what I'm going to explain to you right now is, so it is, let's say, absolutely very technical, but what we want to do is to propose a method that is very, let's say, that has indeed the practical applications, but also has, let's say, good theoretical guarantees. So to do so, let me just explain that it is what I was telling you before, but you can believe me. So as I was telling you, let's say the proximal operator for a convex function is the resolvent for maximally monotone operator, because the subdifferential is a maximally monotone operator, and this problem can be really translated in the setting of, so let's say, studying the space of proximal operators can be translated into studying the space of non-expansive, or let's say one Lipschitz operators. Lipschitz operators with Lipschitz constant equal to 1. Indeed, all proximal operators of convex functions are here, but not all the functions here are proximal operators of convex functions. Indeed, this space is bigger. But there is this equivalent. So what we're going to do is to study, let's say, the problem that we want to study in this space here. So, okay, now I'm going, let's say, in order to, let's say, introduce this concept of learning, what they want to do is, let's say, to introduce the problem of supervised learning via some drawing that I did by myself. With this drawing, but indeed, this was very well explained by Luca yesterday, and I will take that information for my advantage. So the idea is that you have a bunch of points in the space, and you know that these points are, let's say, they have a law. In a more technical way, they have a probability distribution. but this probability distribution, F, you don't know it. So what you want to do is that you want to kind of find a function which not exactly interpolates the points, because this leads to overfitting, but to is, let's say, as close as possible to all of them, since you also want this function f tilde to be able to, let's say, predict future values of your. So if you receive a new pair of points, you also want this function to be useful for future instances of the same, let's say, of the same problem. This is from a drawing point of view. From a theoretical point of view, you have a pair of random variables and you want to solve, let's say, the expected loss with the square error among the space of non-expansive operators, but by only having access to a finite training set. But absolutely, of course, you know that this bunch of training sets are, let's say, are distributed, independent and identically distributed as the random variable that you have. So, from a practical point of view, what you do is that you solve, let's say, or you try to find the minimizer of the empirical error. So let's say, from what you try to do is that you try to find the minimizer of a finite version of the expectation that you were considering above. So typically, this finishes here. So you solve this problem, and that's it. The main issue of this thing is that, of course, the space of non-expansive operators is an infinite dimensional space because it is a space of operators, and therefore this problem is unfeasible. So what they want to do now is to say, so once you fix the number of training points, what they will do is to find, let's say, an approximation space where this problem becomes more tractable and where you can compute the minimizer of an approximated version of this problem. And then I will try to prove that this minimizer converges, in some sense, to the minimizer of this problem here. So you have to remember EP. Okay, so the first step. I have in mind that I have a bunch of points here, a bunch of training points, okay? So the idea is that I have my bunch of training points in the, let's say, of x size, let's say, in the space. One can think always of in R2. And let's say, you want to, so you put your points in the space and you want to, let's say, maybe the drawing is better. You have your points in the space and you want to find, so you want to triangulate the space. So you want to, if you can, it's written simplex everywhere, but you can think of triangles always. So you want to consider it the convex envelope of the points, which is, let's say, the outer part. And you want to, let's say, partition the space. You want to, of course, partition it. The properties, I have to say that they are not necessary, they are not interesting, but you just want you want it to have this shape. You want the triangulation of the points to have a nice shape, let's say. Okay, so this is the first step. The first step is triangulating the space. The second step is that, so you give me a point and they can tell you in which triangle that such point is contained. So if I have the point inside the convex envelope of your training point, I can tell you in which triangle it is. Okay, once this is done, this point inside the triangle can be written in this way, where these parameters lambda I are called barycentric coordinates. They are super nice because they are non-negative, and also they sum up to 1. And of course, you consider here d, which is the dimension. And as you can see, it's a linear combination of all the points. And then, so once it is fixed, what you do is that you define your operator in the convex envelope of the point as the image, as let's say same equation, but as the image of the point through n. This image. So the nice thing is that there was, let's say, a condition on the input point, but let's say there is no condition on the output point. So this n of xi can be whatever the ones you want. You don't have any kind of conditions on them. And therefore, once I have defined the operators that I want to construct, I have already defined the space. Let's say the space where I want to approximate. Well, yes. Well, okay, maybe I lied to you a bit. So it's not exactly the space. So I want to, let's say, approximate in the space of piecewise defined operators in this triangulated space of training points, but they also want to intersect it with the space of non-expansive operators. So the solution of this problem. So this, you have to believe me, and I will show it to you in the end, that this is a finite dimensional problem already when you are doing this. And the solution of this problem will be an operator which is non-expansive, and it's also, let's say, have this piecewise defined structure in either simplices or, if you want, triangles. The problem, let's say, one of the main issues that this problem has is that, first of all, I have to kind of prove why I am saying that this problem is finite dimensional, and then I have to also kind of say that this formulation is not a very, let's say, computational friendly, in the sense that it's not very easy to, let's say, tell the computer to solve this problem here, because indeed it's an intersection of spaces, it's a mess. So the idea and the thing that they want to do now is that they want to tell you that, so I want to, let's say, kind of translate this problem into, let's say, a more tractable way by only considering conditions on the training set of points. So the thing is that if you, again, we start here, we start with a point in the convex envelope, and you can believe me that so the n of x, the operator here, can be redefined in this way by considering these matrices here. I mean, if you sit down, you can do it in 5 minutes, and you can write it in this way, where these matrices A and B are, let's say, the matrices with the, let's say, linearly independent d directions of the problem. Let's say of the triangle where you are inside, and be the same but with the images. And then once you have written it this way, you may ask yourself why is it interesting to have it here? And it's because of this lemma, which has been, let's say the first step, which tells you that if let's say if the derivative of the operator n is less or equal than 1, then the operator itself is 1 digit. This is a consequence of a theorem which is called the Rademacher theorem, but of course it's let's say it's Lipschitz version. So if you have that the norm of the operator the norm of the derivative of the operator is less or equal than 1, then you get that the operator is 1 Lipschitz. And finally, so we have found a condition. So we have characterized the set that we had before. So we have characterized this set here, and we have been able to, let's say, to write it in a finite dimensional way via this, let's say, via this condition on every triangle. Of course, this condition is for every triangle. So therefore, we have found a finite formulation, let's say, more readable and more tractable for a computer for such problem. Okay, what they wanted to tell you at the beginning was that, so I told you that the idea was to prove that this let's say that this problem was converging to a solution of the empirical problem that they had at the beginning. So to do so it's stated in dimension equal to 2. I have to say that the problem is also true in higher dimensions. It's much more difficult to explain, but since I wanted to be truthful, I just wrote equal to 2 because it's the text that will appear here. So there was this idea of simplicial partitions where you have this let's say bunch of points, and you want to kind of triangulate the set of points. And in this case, we think of the same thing, but we think of a sequence of simplicial partitions, which is, let's say, adding points inside the triangulation, and every time you add points inside the triangulation, you retriangulate again. So the idea is that you make it every time finer and finer. And the idea is that if you define, let's say, the minimizers for every k of this problem, and you consider this sequence of minimizers, then there exists a subsequence of this that which star converges to a solution of the empirical problem that I was telling you at the beginning. In order to, okay, well, this is the theory is done. In order to let's say to explain so what did we do with the experiments, the idea is basically that instead of, so we are incorporating the regularization function in this way, in the sense that we assume that there is this differential, let's say this finite version of the differential here, and we assumed that the function has this kind of separable structure or summable structure. Since this is very interesting in order when you want to compute, let's say the prox of it, and the main example of so this happens. So this is not something that doesn't happen. For instance, this happens with the square norm. If you consider the differential of the square norm, it has this separable form, and if you compute such proximal operator, you realize that you are computing the same proximal operator in the n squared direction. So this was let's say one of the first experiments that we did, where you have the real image, the noisy image here, and absolutely these are not, let's say, state-of-the-art methods, but we want to, let's say, illustrate that the learned proximal operator that is here, that is the one that we defined, is, let's say, a combination of, let's say, both the smoothing capabilities that the square term has, but also, let's say, of this piecewise, how to say, of these properties that the classical, let's say, total variation norm has. Thank you very much.
Thank you, John, for the nice talk. Are there any questions from the audience?
Thank you very much. I have many questions. The first one is, it's very interesting. The first one is the proximal point operator is not only non-expansive, is firmly non-expansive.
Yes, indeed.
So maybe you should also, let's say, minimize not on the set of non-expansive operators, but on a smaller set.
So this is, so indeed there's this characterization, right? So if you have a firmly non-expansive operator, you are uniquely, let's say, characterized by the space of non-expansive operators via this formula. So for every firmly non-expansive operator, you have a non-expansive operator. So the idea is that at the beginning of the project, the whole thing was stated from, let's say, the firmly non-expansive point of view. But we realized that it's, let's say, much easier to work on the space of non-expansive operators. The experiments are easier, also the theory. So it's much easier to work with when you are working with one matrix operator. And I have to tell you that there is no theory about the non-expansive operators still, and I cannot even imagine how the theory is for non-expansive operators.
So at the end you are learning n, not t.
So if I have n, I get back t, and I can also construct, let's say, the maximal limit, so the resolvent of the maximal limit operator. So I go back.
And the second question is, for the first problem that you presented, so around slide 6, maybe before, sorry,
So
slide 5.
This one?
No, before, sorry. For the example with which you started. Okay, for this one, what are the data?
No, so here there is no data.
No, I mean, when you want to learn T, what are the couples xi?
So here is, okay, so here you incorporate, so they are built for the first time here. So the couples xi, yi should be, so in this case, x is the variable which is noisy. So I know this was a mess, but the x is the variable, the image that is noisy and that you want to denoise with your operator n, and yi's are in this case, let's say, the original images. So are the original images. You have a bunch of, so they are, let's say, you can say that they are switched. You're noisy, so these are the noisy and these are the original ones.
but it's a little bit more complicated, you know, because if you want to learn only the prox, then there is the part inside that is x minus gamma, no?
So let's say I am not learning a proximal operator. I am learning an operator which is the resolvent of a maximum monotory operator, which belongs indeed to a much more general class. Indeed, one can think of it as a much more general case. So you are learning as an operator which is much more general than the prox of a convex function. But indeed, you are not learning and not exactly learning a proximal operator.
Someone else?
If there isn't anyone else. And you have convergence to the piecewise affine problem to the, let's say, empirical risk.
Yeah.
And do you have rates from the empirical risk to the expected risk?
No. This was not.
Because this is also interesting. It should, maybe it's classical, maybe it's not, because the space is a particular space, the space of non-expansive operators. Maybe you can get something better, I don't know.
We haven't thought about it. It could be a follow-up project indeed.
So let's say the convergence of n hat 2 and star. Okay.
Indeed.
If there are other questions, you can ask him during the coffee break, because we are slightly late. So let's thank Jonathan again.